And I thought today I'll just discuss about the basics. So starting with about our chemistry, our choice, no, we all have taken up chemistry and how we have got into this. And now I think teaching has become a passion for all of us. So let us get into that. So I thought first we'll go into the basics of organic chemistry, which no, even if it is in class 12, first we'll have to brush up that so that the children get into, become thorough with that. Only then they can go in for the other aspects. They'll understand the remaining topics. So I'll just start with sharing my screen. Yes, teachers. So we are going to start with general organic chemistry and then go into whatever we can complete today. Let me see. Haloalkanes, haloarenes. I'm just going to touch upon the main ones. We are not going to talk in detail. So basically, all of us chemistry teachers, first when we introduce chemistry to our students, the thing is chemistry is everywhere around us. Wherever you go around, any aspect is touching, is dealing with chemistry. So that's what I think the first introduction we can give to a child when she or he is solely going into studying the subject. And the various branches of chemistry, so many branches, but when it is in class 11 and 12, we are just concentrating on the physical chemistry, organic chemistry, and inorganic chemistry aspects. Though others, theoretical and all, to an extent comes under this, but we mainly deal with these three branches of chemistry. And I just thought this is an apt example here when we come in. The 2021 Nobel Prize in Chemistry was given to two scientists for the discovery of organocatalysis molecules. So I thought this is apt when we are going to discuss haloalkanes and haloarenes, where we are going to discuss about stereochemistry, enantiomers and all that. So all of you would have gone through this. So just thought I'll put up a slide about this. So how it's related to the organic chemistry part. And basically, what is the need for today's workshop or the 10 workshop sessions that we are going to go through? What is the need for it? Every teacher, is it not, is a seeker of knowledge. So we are in a process of continuous learning. Once you got into the profession of teaching, doesn't mean we are just going to teach whatever is there in the book to the children, that's over. Nowadays, every child is different. How you have to put across the subject concept to the child, each child, it will differ. So we have to learn different methodologies, new ways of approaching the child. So we are in a process of continuous learning. So both teaching and learning are inseparable part for us. And continuous learning leads us to gain more knowledge, will help us to grow in our profession. Then assessing students, the different ways of assessing students will help us to understand what is lacking in our way of conveying to the children, what are the new ways that we can improve. And for the past, with the pandemic situation, we have learned so much, is it not? From what we thought we could use only a blackboard and chalk for teaching, we have come in to use technology. So I think this blended learning is to stay. So we have a lot of opportunities to convey, give more ideas, more presentations to the children. With blended learning. So, and I think that will be going ahead. And the course objectives are all these. And pedagogy that will be going in is to understand the conceptual learning goals, then try to spiral the curriculum, make connections to what the student already knows, and based on that, develop on the future new concepts. And give them guiding questions, engaging questions, so that their previous knowledge is tested. And from that, you can build in new concepts and the child begins to understand and learn with interest. And basically, when chemistry comes, chemistry is often called as the central science, connecting mathematics, physics, all the other core science subjects. And whenever a thought of chemistry comes, all of you, most of the people, even every layman thinks suddenly they relate it to research, labs, all the mixing of solutions and all that. But chemistry lays everywhere, is it not? Everything around you is chemistry. So it's not just concentrated to the labs or anything. Anything, any person whatever you touch is having chemistry in it. And learning chemistry, there's a lot of new information that the child has to learn, and some of the aspects has to be memorized. But memorizing doesn't mean just rote learning. So they have to first, or what we have to do, or what we have to train the child is to first focus on gaining understanding. The child should understand what is being taught, and only if the child understands, memorizing is effective. Otherwise, just rote learning will not help. So a child has to understand the concepts, and it's our duty to put it across to the child in a way that the child understands. So these are the things that we will have to go across. And basically, to help them understand chemistry, it has been suggested that they have to work at 3 levels. The macroscopic level, which is the observational level, where you do your experiments, where you can see things, the color or the precipitation, all that's happening, the experimental part, which is observable, the change in pressure, volume, all that is called as the macroscopic level, while the submicroscopic level is the atoms, molecules, ions, and all that we discuss, the 3D models that we discuss. And the third level is the symbolic level, which will be involving all the equations, etc., that we write to gain understanding of the reactions and all that. So put together, the 3 macroscopic, submicroscopic, and symbolic level is called as the Johnston's triangle, and it is represented in this way. So the one on top here, this is your observational part, which is the macroscopic level, and this part, this edge corner, which deals with the particles, atoms, ions, all that will be the submicroscopic part, and your equations and all coming at this part is the symbolic level. So the Johnston's triangle represents how you need to understand chemistry. So this is it, the macroscopic observational level, all that you observe, the changes that you observe. Submicroscopic or the particle level is all these that you observe around you. And the symbolic level is the formulas, the equations, calculations, all the writing part of that goes into it. Is these are the 3 parts of the Johnston's triangle, which helps us to understand the concepts in chemistry. And the way you can approach, how you can teach your students and make learning of chemistry easy, is to bring in friendly presentations. That's the main aspect. If that goes into the child, he'll be able to grasp the concepts very much. Secondly, is to use analogies wherever possible, illustrate, give examples, they give related to simple examples around you. So that's illustrating with analogies and correlating with everyday life aspects. Wherever you can bring in all these 3, learning of chemistry, understanding becomes easy. Any abstract concept also can be made clear by using these sort of teaching methods. And basically, when we introduce organic chemistry to a child, what do we talk about? Organic chemistry, the compound made up of carbon, hydrogen elements, and along with that, some heteroatoms and all that. And initially, organic chemistry was named because it was thought it is only naturally occurring, and later on artificially synthesized organic compounds have been developed, and the name still remains. So basic concepts. So when it comes to starting with chemistry, so even if it is class 12, class 11 students, in class 11 we usually rush up portions, but I think now with the new curriculum, where the chapters have really been reduced in class 11 and class 12, though I have to say inorganic has been completely removed, which is not a very good balanced way. So I think we'll now have time to elaborate on all the concepts even in class 11, but still when the child comes to class 12, there's a lot of organic chemistry chapters coming in here. So we'll have to revise the concepts that we have started up with in class 11. So the very first thing we have to discuss, I think, the classification of organic compounds into a cyclic, cyclic compounds, and the further divisions. This is only the basic aspect. I think this the children will be knowing. We need not deal or go deep into this in class at class 12 level. Then writing the formulas, because that comes even in class 12, where you have to write the structures, where you have to write the, give the IUPAC nomenclature and all. So the different formulas, the empirical formula, the molecular formula, the condensed formulas, structural formula, bond line formula. We can start revising. We can give a few examples when we start with the first chapter so that the child recollects all the different ways of writing the formulas of compound. Then coming on to nomenclature part. So very first thing about identifying the parent chain in a compound. What are the functional groups in a compound? What are the branches which are to be taken as the branches? Which is the principal functional group? All this has to be properly, the child has to be guided to learn all this properly. And also very often we come across branches where we have the isopropyl or the secondary butyl group. So instead of going in for IUPAC naming, if the child knows how to name this in the trivial name category, this is accepted. So I think we should make the child thorough about writing the structures and naming in this common naming way. And then when it comes to the IUPAC naming, a complete name. First, we identify the word root. We have to go in to identify the word root. And then after that, the prefix and the suffix terms. So suffix is made up of two components. We have the primary suffix and the secondary suffix. The primary suffix, which helps us to understand whether the compound is saturated or unsaturated. The secondary suffix, which helps us to identify the principal functional group. The name ends with the name of the principal functional group. And prefix, again, can have a secondary and a primary prefix. A primary prefix may not always be there. It comes in only if your compound is cyclo, and bicyclo and spiro anyway is not coming in normal class 12 CBSE boards. So if it's a cyclo compound, we will have in a primary prefix. If not, we'll be having only the secondary prefix, which is for your substituents, alkyl substituents, or some functional groups which are always substituents, or the secondary functional groups. And to that, we have to attach the locans also. At the suffix level and the prefix, if you have the locans, that also has to come in. So this naming, a child has to understand, because we'll have multiple functional groups in our nomenclature. In most board exams, we have seen at least 2 functional groups maximum and not beyond that much with multiple bonds and all that. So if it is a multifunctional group or with substituents, the child has to know how to name it correctly. So I think once they come to 12th, we start with the chapters. We can give a few nomenclature exercises to the children as assignments so that they brush up what they have learned in class 11. So like for an example given here, we have all this included here. So I thought I'd take this as an example. So a word root here with 5 carbons is pent. And the primary suffix coming in is AN, indicating that there is no unsaturated, it's a saturated compound. So An, En, Yn comes in the primary prefix based on whether it's a single bond, double bonded, or triple bonded compound. And we have a primary suffix, secondary suffix here, indicating our principal functional group as the keto group, double bond O. We have 2 functional groups here, hydroxy and the keto group. So the hydroxy group is a secondary functional group when you have keton here. So, and we have this cyclo, it's a cyclic compound, cyclopentane, and hence we have the primary prefix coming in. And also we have the secondary, because we have an additional functional group which is secondary here. The hydroxy comes in as the secondary prefix, and the locant 2 attached, indicating the position of the hydroxy functional group here. So this is one example where it's exhaustive, giving you complete rules coming in here. The word root, the primary prefix, primary suffix, and the primary prefix and primary secondary prefix with the locant. And also in additional where we have to use, where we have to add a and all that, all those rules, everything comes in. So I think all of us, it'll be fine if we give a few exercises to children so that they refresh and come back and they have a thorough knowledge of naming, so that we need not go in for every chapter, we need not again reteach the nomenclature once we initially start off with this.
Ma'am?
Yeah?
If an organic compound carries a double bond as well as a OH group, children normally getting confused which has to be given first, ma'am.
And priority is for the functional group, ma'am, as I have put up this slide also. Then comes multiple bonds. Always okay. Functional group is given priority, followed by double bond, and then comes triple bond.
Okay, ma'am, okay.
Yeah, and the following alkyl groups or aryl or the halogens, nitro group, alkoxy, the ether part, always are prefix substituents. So they never come as a principal functional group. So this we are already teaching children, but I think this in class 12 also we have to give them an idea and tell them to get back to this, and they have a thorough knowledge of this, because that confusion always comes in. The children keep on asking, is it a double bond, is it a triple bond, or is it any of this? That's what. So they should be learning this once again. We have to give them this input. So a basic, just a slide on the different functional groups. All of these are not needed for class 11 and 12, but basic things we do require. So we should train the children in that part. And another important aspect is for the child to understand what is a methyl, what is a primary carbon, secondary, tertiary, because we'll be using this quite a lot in the coming chapters. So they should have a base about what is a primary carbon. You can relate it to the number of hydrogens attached to the carbon or the number of alkyl groups. You can teach the child in any of the way the child is able to remember, able to understand. Is it based on the number of alkyl groups or the number of hydrogens? So this is another important aspect which a child has to know, has to understand if he or she has to proceed further to understand the concepts in chemistry. Then isomerism, basics of isomerism is also needed, where you have all the chapters related, where we can have chain isomerism, we can have position where the functional groups are coming on different carbons, functional group isomerism, when we are talking about alcohols chapter, alcohols and ethers, functional isomers, aldehydes and ketones, functional isomers. Metamerism, when we talk about ethers, we will have to discuss about metamerism. Tautomerism, not much coming in here, but still, because we have the alkyne reactions for the preparation of aldehydes and ketones, children have to know what is the process of tautomerism, what are tautomers. So all has to be refreshed. And geometric and optical isomerism, geometric alkene additions, and optical, especially in chapter of haloalkanes and haloarenes, we have to discuss a lot about optical isomers. So we have to brush up on this also. The slide with the examples here. Chain isomerism, position isomerism, and functional group isomerism examples. Geometrical and optical isomerism. So this chapter will be dealing with optical isomerism. So this is also an important aspect of organic chemistry. And another main thing which a child coming into 12th should be thorough about is to understand the fundamental concepts of the reaction mechanism and what are the displacement effects. So always, what is considered as an organic molecule, the substrate and attacking reagent during the course of the reaction. Usually the one which is considered the important main one is, even if your attacking reagent is also a carbon containing compound, then the one which is of more importance is considered as the substrate, and the other one is considered as the attacking reagent. And you will have reactions in which most of the cases you have an intermediate being formed, and then that's converted to products with a lot of byproducts. Other byproducts may or may not be there. So a basic structure for an organic reaction coming in. And what you call as a reaction mechanism. And class 12, we have a lot of mechanisms that the child has to understand. So he has to have an idea about all this to understand the mechanisms of the reaction. Yes, teacher. So after that, what type of bond cleavages happen during an organic reaction, where we can have the covalent bond breaking in two ways. One is the homolytic cleavage, where you have both the two electrons of the covalent bond, each moving on to one of the atoms. A gets one electron and the atom B gets one electron. That is homolytic cleavage. And homolytic cleavage results in the formation of a free radical. So free radicals are generated during homolytic cleavages. So what type of reactions generate free radicals? It's a lot where we have free radical mechanism, halogenation in this chapter. So a child should be knowing all these basics, in which case is a free radical generated, in which case are carbocations, carbanions generated. So next type is where we have an heterolytic cleavage, where the bond electrons go to one of the atoms and the other one is losing the pair of electrons. So the one which gains the pair of electrons having the negative charge, and in case it's a carbon, we call it as carbanion, and the other one as the carbocation. When it becomes the carbon, if it is losing the pair of electrons, carbocation. So mostly we'll be dealing with such cases. And the stability, so the three carbon intermediates that are formed during the course of a reaction, carbocation intermediate. So where the hybridization is also shown here. So when we teach children, I think we do that in class 11. So this is applicable to a student going to come into class 11 also, how we have to go in. We have to teach the hybridization of the carbocation intermediate sp2 with the empty p orbital, the third p orbital being empty. And a methyl free radical or the carbon free radical generated will also be having sp2 hybridization with one electron present in the unhybridized p orbital. And when it's a carbanion, you have the sp3 hybridization with the extra pair, the lone pair of electrons present in one of the sp3 hybrid orbitals. So telling the child or making the child understand with respect to the hybridization. And then comes the stability of these three. So carbocation stability, very important, because we come into class 12, all of the chapters where we have intermediate formations, where we have carbocations and all being formed. So the child should have a clear idea about the stability of carbocations, carbanions, and carbon-free radicals. Only based on that, the child can go ahead. Otherwise, the child cannot memorize mechanisms. If he understands this concept, he'll be able to easily understand and go about understanding the concept of the mechanisms. So stability of carbocation and carbon-free radicals, tertiary being the most stable, followed by secondary, primary, and methyl. And in the case of carbanions, because of the different effects, the primary being more stable. So all this we have to deal in detail. And the electron displacement effects, the permanent electron displacement effects, inductive effect, where we have the plus I and the minus I effect, and the resonance effect, also called as the mesomeric effect, and the hyperconjugative effect, hyperconjugation coming in, and the temporary effect seen in compounds with multiple bonds, the electromeric effect. And in most of our study of further reactions, we'll be dealing with more of inductive effect and resonance effect. So inductive effect, what is plus I effect, what is minus I effect, has to be clearly conveyed to the child. Similarly, resonance effect, when it comes to in aromatic compounds, resonance effect, we have to discuss about groups which are plus R groups and minus R groups, because when we have to have substitution, electrophilic substitutions during the reactions, the child should know the presence of that group will lead to ortho-para substitution or meta substitution. So we have to give a clear idea about all this to the students. So I think once they come into 12th, a clear idea at least about the inductive effect and the resonance effect has to come in. And then the types of reactions. In class 11, we don't deal much with the types of reactions, but in class 12, we go deeper into all of this. So we have the addition reactions, where we go in for nucleophilic, electrophilic, and free radical addition reactions. Not much about concerted, we don't discuss as such. Single step bond breaking, bond formation, all this coming in. Substitution also, we have all the three categories that we'll be dealing with: nucleophilic substitution, electrophilic substitution, nucleophilic, especially now in the chapter of haloalkanes, where we're going to discuss in detail about SN1 and SN2 mechanisms. Electrophilic, where we have electrophilic substitution reactions of in the aromatic ring, free radical substitutions coming in halogenations, all this comes in. Elimination, though we discuss elimination, we are not bifurcating and studying in detail about E1 and E2, not at the class 12 level. Rearrangement, we do have examples of 1,2 rearrangement, 1,2 hydride shifts, 1,2 methyl shifts, and all, where whenever there's a possibility of carbocation stability, we have some questions related to all this. So we have to discuss about all this: addition, substitution, elimination, and rearrangement reactions. And the other important aspect is about nucleophiles and electrophiles. Nucleophiles, how you can relate it, how you can give examples to the child. Nucleus, loving; phile, philic, the word loving, and the example cited for nucleophiles. Similarly, electrophiles, give all the possible common examples so that the students are thorough with all those, and give the example of how do they attack, which is the electrophilic center. A nucleophile will attack an electrophilic center, while an electrophile will be attacking a nucleophilic center. So all this clarity should be given to the child. And further, about when we're talking about the substitution, different examples of where you have nucleophilic, electrophilic. So substitution reaction, where we have, it's a nucleophilic substitution reaction. Haloalkanes, adding on hydroxide ion, nucleophilic substitution reaction. Nitration of benzene, coming under electrophilic substitution. Halogenation of alkanes, an example of free radical substitution. Under addition, you have nucleophilic addition reactions, carbonyl compounds. Most of all the carbonyl compounds, we talk about electrophilic addition reactions, with carbon getting a positive charge due to the electron shift towards oxygen. So carbonyl compounds are showing nucleophilic addition reactions, and quite a lot of reactions that we have to learn, child has to learn under that lesson. Alkene, addition of hydrogen halide to an alkene, is an example of electrophilic addition reactions. So where H+, the simple proton, gets added on, that's the rate determining step, and hence we call it as electrophilic addition reactions. And free radical addition, you have, though the chapter polymerization is removed now, but we do give them some examples of polymerization and all that. So addition polymerization, where we have the free radical mechanism coming in. And elimination reactions also we are talking, but teaching, but elimination, we are not going into in-depth of the mechanism. We are just talking about conversion of alcohols or haloalkanes and all into alkenes. So those also a few examples here. So that was the basics. I thought we'll just brush up before going into the class 12 chapter. So I think we'll just brush up. Yeah, so we were talking about from alkenes. So specifically why HBr, why now we were discussing about using the benzoyl peroxide coming in. And then coming on another one where we get the dihalo substituted from alkenes can be converted to dihalo compounds. How is it possible, teachers?
By addition on an alkene.
Yeah, which reagent do we use for that? When we are converting in Zoom, it is very difficult to skip between screens. Yeah. So if I have, when we are using bromine water, yes, bromine water, we are getting, what sort of a halide do we get?
Vicinal dihalide.
Vicinal dihalide. So to prepare vicinal dihalides, we can go in for halogenation. And this is also a test for, we will describe, we will explain to the child, to the students when we teach this again, that it is a test for unsaturation. I do have some link where there is a video to show the bromination and all that. I'll give the links later. So y'all can also know when we teach the students. We can show that also nowadays. There is a possibility of blended learning. We have AV rooms in our schools where we can take the children and show them all that. So bromination, vicinal dihalides coming in. HX addition is where we are getting halogenated compound, monohalogenated compound, and so on. And coming on to haloarenes, so we tell the children, like alcohols, from alcohols we are using it only to prepare haloalkanes. We cannot prepare haloarenes from alcohols. So there is where we stress about the difference in the CX bond nature of aliphatic CX and aromatic CX case, no? Aromatic ring with the X bond. So there we stress about what all do we teach the child when we go in for this one.
Partial
Why
double
are they
bond
not
character.
showing the normal reactions, preparations?
Partial double bond character.
Yes.
sp2 carbon atom.
We talk about partial double bond character, and yes, teachers, what else can we talk about? Why the partial double? I'm sorry, I've shown the C separately. It is on this ring. Yes, CX bond. So it has a partial double bond character. Why does it have the partial double bond character?
Resonance.
Delocalization ability.
Resonance.
Due to resonance,
Yes, we have to discuss about, is the board screen seen, teachers?
Yes.
Yes, ma'am.
Yes, we have to clearly tell the child about the resonance effect here. So that's what I talked about, having clarity. The child has to, we have to refresh regarding the resonance effect and all that. So where we talk about the electron transfer lone pair, and this is the reason why it is getting a double bond character. So all this we are to explain once again to the child, because the child might have forgotten or not taken it in class 11. The child is learning so much of chemistry for the first time. So retaining becomes difficult. So we have to bring in all this once again. So one is the partial double bond character. And the other factor we can talk about is, what about the C here? It is a sp2 hybridized carbon. So we have to also talk about the, what do you say?
Bond.
The electronegativity of the carbon, right? An sp3 carbon, an sp2 carbon, and sp carbon. We have to stress upon the electronegativity difference, and based on that, so sp3, sp2, sp carbon, we have to stress upon the fact that an sp carbon is more electronegative than an sp2 carbon, than a sp3 carbon. So based on that, the bond polarity differs. So CX in a straight chain where we have an sp3 carbon, and CX where we have an sp2 carbon. So based on this, how will we explain, teachers? So one, you had mentioned about double bond character. Now based on this, the CX bond.
Shorter the bond, no? sp2 bond.
Yeah.
Carbon having sp2 character will form a shorter bond with the halogen.
Shorter bond, yes, that's what, because the electronegativity difference decreases, whereas here it's more X minus is, X will be more electronegative compared to the sp3 carbon. So here the CX bond will be having shorter, it will be a shorter bond because carbon is also electronegative compared to an sp3 carbon. So we can cite both the reasons here. We can talk about the Plassard effect, giving it a partial double bond character, and also the hybridization of the carbon to which the halogen is attached, making a difference. So I think we have to give both the points here when we talk about the, what do you say, why less reactive to, why it does haloarenes not, why are haloarenes not formed by these methods. So haloarenes, therefore we discuss about preparing from say benzene. So what is the difference? Benzene being converted to chlorobenzene and methane being converted to chloromethane. What is the difference in the reagents? Yes, teachers, let us discuss. Because that's again where children will find it difficult to remember the difference in the conditions. So when we talk about methane being chlorinated,
Just free
That is in the
halogen,
presence
free radical
halogenicity.
halogenation.
Halogenation happens in presence of
Sunlight.
light. Yes, we require light or very high temperatures where it is undergoing a free radical
Dark
mechanism. That's what. But when it comes to aromatic compounds being converted, there what is the
Dark-
difference in condition? That,
Absence of light, ma'am.
yeah, it happens in absence of light. And in addition, what do we require?
Electrophilic
Louis
substitution
acid.
happens.
That's an electrophilic substitution, yes. And it happens. What else
Louis
is required there?
Louis acid.
Will
Louis
be
acid.
requiring Lewis acid. Yes, requirement of a Lewis acid is very important here. So when it comes to aromatic reactions, aromatic substitution, for example, chlorination, it happens in dark conditions and in presence of, say, a Lewis acid catalyst. Even iron can be used. Iron will first react with chlorine to convert ferric to ferric chloride, and then that. So here, what is the mechanism happening? The difference mechanism also differs. Now, in the case of aliphatic, when hydrocarbons undergoing halogenation, there it is a free radical mechanism where we are getting a mixture.
Yes, ma'am.
Whereas here it undergoes a
Electrophilic substitution.
electrophilic substitution.
FeCl3 will abstract Cl minus ion, madam.
Yes.
It will form
that's what.
FeCl4 minus.
So we are getting our electrophile formed will be Cl plus here, right? Cl plus
Yes.
electrophile is generated in the presence of Lewis acid catalyst, whereas in presence of light, here it's undergoing homolytic fission. And here it is a case of heterolytic fission of chlorine, and that is getting attached to the electron deficient ferric chloride. So these are the points which we have to stress upon when we teach children. Everything is new to them. So the difference in the case of aliphatic compound, hydrocarbons undergoing halogenation, and aromatic compounds undergoing substitution on the ring. So the same thing when it is, if it is toluene, if we are going in for chlorination in light, and if we are going in for chlorination in the dark conditions. So this is one example which we can give the children to differentiate, make them understand how to go about this one. So if we are using chlorination in light, we'll be having it as
Aliphatic.
Benzyl chloride, madam.
yes, we get it as
Benzyl chloride.
benzyl chloride. We get it as benzyl chloride, whereas when we are going in for the above example, say another Lewis acid catalyst, aluminium chloride, here we are going to get,
Ortho para.
yes, we get both ortho and para substituted compounds. And in most of the compounds, the para one, which is of major product usually. And separation of this is also, in the case of, what do you say, hydrocarbon halogenation mixture, methane chlorination, we are getting different products. Separation of them is difficult. Whereas in the case of aromatic ortho para substituted products, they differ much in comparatively in their boiling points. So they can be separated by fractional distillation. So it's an efficient method. So these are the things about the preparation. And the other one, that is another name reaction coming in, which is that, teachers? Starting
Sandmeyer
material,
reaction.
yes. From diazonium.
Sandmeyer reaction, madam.
Sandmeyer reaction coming in. And so diazotization. So first we'll have to teach the children what is diazotization. Aniline in presence of nitrous acid. And nitrous acid basically in situ production from sodium nitrite and HCl, and the temperature conditions, cold conditions of 0 to 5 degrees that we talk about to generate this. And this is what is Sandmeyer. Sometimes children think even the first part, that is diazotization, also comes under Sandmeyer. So that's diazotization. And from diazonium halide converting to chlorobenzene, bromobenzene, these are coming under Sandmeyer reaction. And even nitriles, is it not? CN, C6H5CN coming in. All these come under Sandmeyer's reaction. So these are the parts that we'll be. So here, when we cover preparation of haloalkanes, 3 name reactions are what the child learns, Finkelstein, Schwarz, and all that. So
Ma'am, your Gatterman reaction also there. no?
yes, Gatterman reaction. Yes, sir. Gatterman reaction also. So when that's the difference, another point of difference, no? When we tell the children, Sandmeyers, we are using cuprous halide in HCl or cuprous bromide in HBr. Or even cyanide. Now, since this is the chapter whereas when it's Gatterman, it's only the difference in the reagent, copper powder in HCl or copper in HBr. So the name of the reaction changes. So Sandmeyer and Gatterman. So that part. And talking about production of iodobenzene. Iodobenzene, we just need to,
Potassium iodide.
yes, we just need to warm with potassium iodide. And fluorobenzene is entirely different, right? Fluorobenzene, aniline has to be first converted using,
Fluoroboric acid.
yes,
Fluoroboric acid.
HBF4. Fluoroboric acid is used, whereby it's converted to N2BF4. And then we just need to warm it to convert it to fluorobenzene. So that doesn't come under Sandmeyers. So iodo and fluoro production is not coming under Sandmeyers, whereas chloro and bromo benzene is either by Sandmeyer or Gatterman reaction. So this gives us an idea about the preparation methods. So we were able to touch up only on the preparation methods today.